Hello everyone and welcome back to my YouTube channel. I am Varshini V from Sri Venkateshwara College of Engineering, currently pursuing my data science engineering. Today we are going to be looking into a topic from mathematics, and the topic I have chose for today's video is vector calculus. The topics we are going to be witnessing in today's video in vector calculus are going to be introduction to vectors, operation on vectors, gradient, that the operations are gradient of a vector, directional derivatives, divergence of a vector and curl of a vector. And we are also going to look into a few general applications in everyday life of a vector. We all notice this image here, which is an arrow mark like image. So what do you think it is? It is a graphical representation of a vector, where the length of this line segment is going to give us the value of a magnitude or the numerical value of the given vector, and the arrowhead depicts in which direction this amount of force or the magnitude amount of force is being applied. This also contains two parts, that is the head and the tail of a given vector. Head is the arrow mark and the tail is the line that is preceding the arrow mark. We have another image here, which is the representation of a vector in 3D. The previous image showed us the vector line segment, directed line segment. It is called a directed line segment. It is a representation of a vector in 2D. And in 3D, if we look at the axes here, we see that there is an x-axis with y units of the vector, and we see 8 units here and 3 units in the z-axis. We look into the definition of vectors before we discuss the image. Vectors are physical quantities that possess two independent properties, magnitude and direction. So magnitude of a vector, as we spoke, is the numerical value of how much of a certain physical quantity is being applied, and direction, as a simple direction, is in which way or in which direction the force is directed. Any physical quantity which has both these independent properties is considered a vector quantity. They are geometric representation of quantities like velocity, momentum, force and electromagnetic fields. All these are examples of vector. We know that if I am applying a certain amount of force, or if I am pushing one object from here to here, it means that this to here is the amount of force or the magnitude of force that I am applying, and this is the direction, that is from my left to right is the direction of the force that I am applying. So, and because the force I am applying is along the x direction, I will use a depiction for the direction, that is I cap, that is for x axis. And if I am applying the force in an upward direction or downward direction, that is along the y axis, we use the vector component j cap, and if it is in the z axis, we use the component k cap. And how did vector come into existence? When did all the topic and invention of vector occur? In modern form, they appeared in the late 19th century when Josiah Willard Gibbs and Oliver Heaviside developed vector analysis to express new laws of electromagnetism that was discovered by James C. Maxwell. We all know Maxwell for his right hand thumb rule and the corkscrew rule, but when his discoveries in electromagnetism were trying to be expressed and analyzed by the two scientists, Josiah Willard Gibbs and Oliver Heaviside, they developed a new topic in mathematics that we now know as vector calculus. And this is how we have a point related to how a vector is to be depicted or picturized, and we see the red line here. This is a vector. We see that it is a directed line segment. It is directed because it has an arrowhead, and it is a line segment where the length is the magnitude and the direction the arrow is pointing towards is the direction in which the force or the vector is applied in. Operations on vectors. There are some certain basic operations that are performed on vectors that include the addition of vectors, multiplication of vectors, could be scalar multiplication or vector multiplication too. And all these concepts are basic, but we will look into a few new topics that we have come across. The first topic we are going to be looking into is a gradient. So what is a gradient? If we consider phi as a given function on x, y and z, it is supposed to be a scalar function that is continuously differentiable. Then the grad phi or gradient of phi is defined as the partial derivative of phi with respect to x multiplied with the I cap plus partial differentiative of phi with respect to y multiplied with the j cap and partial differentiative of phi by with respect to z with multiplied with k cap is considered as grad phi, which is the short for gradient of phi. So we can see that the input provided for a gradient function is supposed to be scalar, but the output we get is always going to be a vector quantity because we are multiplying x, y and z uh, elements that are going to be depicting the direction, which is the differentiating factor between a scalar and a vector quantity, because the scalar quantities are quantities that have only one physical independent part, that is going to be the magnitude, but in vector we also have the direction. The second topic we are looking into today is directional derivatives. So what is a directional derivative? If phi of x, y and z is a scalar function and vector d of a given vector, then grad phi into n cap, that is where n is vector d divided by magnitude vector d, is called a directional derivative of phi along n. So n cap is a unit vector that is depicting the directional that we are obtaining by solving vector d, that is given directional derivative or a directional vector. So when we already calculate the grad phi, as we discussed in the previous slide, the calculated value is then multiplied into something that we notice here as n cap. N cap is a unit vector. A unit vector is a vector whose magnitude is always 1. So the formula for calculating the unit vector is also provided here, where n cap is equal to vector d by magnitude vector d. Magnitude of a vector, as we already discussed, is the numerical value of a given vector, excluding the directional parts, that is the I cap, j cap and the k cap. So the formula for the magnitude of vector d is not mentioned, but I will let you know. It is root of a square plus b square plus c square, where a, b and c are the magnitudes of I, j and k components of the vector that we are calculating. In this case it is vector d. We square each part, and the sum is we take the square root, which gives a numerical value again without any ijk components, that is considered as the unit magnitude of a unit vector. So there is also an important theorem that revolves around the derivative of a scalar function. So we'll look into the theorem once. So the directional derivative of a scalar function phi at any point is maximum along grad phi. So the statement clearly states that if we are trying to calculate the maximum of the directional derivative value of the given scalar function, it is always going to be along the direction of grad phi. Divergence of a vector. Now let us look into the new topic that we are going on, the third topic, that is divergence of a vector. If vector A of x, y and z is continuously differentiable vector function, then the divergence of vector A, or div A in precise, is defined to be the del of vector A. So this includes a formula that we have to be considering in order to solve the questions related to divergence. But one thing we have to notice here, in the previous two cases that we considered, the inputs were always continuously differentiable scalar functions, but in the concept of divergence, the input itself is already a vector function. So there, when we perform the grad and the directional derivative function, we are converting scalar values into vector values, scalar inputs into vector outputs, but in this case the input is vector and we have to see that the output is always going to be a scalar quantity. So the divergence of vector A, if we are considering vector A, for instance, we will consider A1 I cap, A2 j cap and A3 k, where we can see that A1, A2, A3, as we discussed, are magnitudes, are functions of the sides x, y, z. So they are depicted with the respective I, j, k components. And then we will have, for divergent of A, we are noticing that we are going to perform del of A, which is equal to, that is a representation. This is the representation of div A. Then we can see the formula, that is, it is dou by dou x plus I cap plus dou by dou x j cap plus dou by dou x k cap into A1 I, A2 j and A3 k cap. So when we multiply these, as we can see that it is a dot component, it is scalar multiplication. So you are just going to multiply the I value with the I value, j value with the y value and k value with the z value. When we perform this operation, we will see that we get the answer, and when we perform scalar multiplication, we do not write the ijk components in the next step. So we have considered dou by dou x of a1 as the first component, plus dou by dou y of a2 plus dou by dou z of a3. This formula gives us a result that does not contain ijk or the directional components, which proves that the given output is a scalar quantity. The next case or the operation we are looking into is a curl of a vector. What is a curl of a vector? If vector A of A, x, y and z is a continuously differentiable vector function, then curl of vector A is defined to be del cross vector A. If we notice here too, the input is a vector function, but we have to check if the output is going to be scalar or vector, because when we noticed in the previous slide, in the previous topic, we saw that it was del dot A, which was a scalar multiplication. But in this case, we have del cross A, which is vector multiplication. And vector multiplication usually gives us a vector output. So if we look into a explanation of the topic, we will see that vector A, if it is considered just like the previous time, a1 I cap, a2 j and a3 k, where a1 and 2 are all functions of x, y and z, we see that curl of A, this is the representation del into cross A. We use the topic of determinants over here, determinant of I, J, K components into different partial differentiative of x, y and z in the next row, and we consider the magnitudes or a1, a2, a3 in the third row, and we tend to solve this particular determinant, and we get it as I into a3 with respect differentiation of a3 with respect to y, and partial differentiation of a2 with respect to z, and minus we have always have the in the determinants plus, minus and plus for I, J, K respectively. So when we solve the determinants, we get this particular formula where when the values of a1, a2 and a3 are substituted and differentiated with respect to the particular xyz components here, we will get a quantity or a vector quantity, because we have I, J and K components here, and that output is also going to be a vector quantity. So for the first two cases, we saw that the inputs are scalar and outputs are vector. For the third case, we saw that the input was vector and the output was scalar, and in the curl component, we see that the input and output both are vectors. Now let us look into a few everyday applications of vectors, or we might just feel like, why do we have to know about it? Because we use it as a vital part in our everyday life. We all use GPS or navigation systems. We can see that GPS or global positioning system uses vector calculus to determine the position of a receiver's on the Earth's surface. The satellites in space that we have sent for the purpose of GPS or in navigation systems, what they do is they emit radiations, and based on the direction and the angles and coordinates of this, the satellite is able to locate where we exactly are. It could be in booking a cab or finding a place on Google Maps. We notice that the current location is usually takes our current location automatically. That is happening by the use of a very vital mathematical theorem or the practice, that is vector calculus. It involves calculating vectors representing distances and directions from satellite to the receiver, and then using techniques like integrations to find the exact location of the person that is trying to use these applications. So this is one important application of vectors. The next general application of vector is going to be in electric circuits. When we notice electric circuits almost everywhere around us, we all use electricity as a vital energy in our everyday lives. So vector calculus plays a role in analyzing electric fields and currents in circuits. For instance, Gauss law of electric fields involves integrating electric field vectors over a closed surface, which finds the total electric flux, which helps us determine the net charge enclosed by the surface. We have all studied about electric flux and Gauss law in our previous what do we call PUC and all of that. So we can see that in the picture clearly that we are considering a positive charge which emits radially outward, and the direction and the magnitude both matter over here, that is the magnitude of charge and the direction the field rays are traveling. We also have a pair, that is a couple of plus and minus charge, where the flow of electric field is happening here, which is also represented and calculated by using the concepts of vectors. And the next application is going to be in graphics and animation. We all know that graphics and animation is a growing industry in the current day. It could be anything from Disney's Pixar movies and other movies of them. One important and example as we can take is going to be the Tangled movie, the story of Rapunzel, where the animation of hair included a lot of vectors in it, because Rapunzel had this long hair and she had to, the animation of long hair has always been difficult, so we notice a lot of characters having shorter hair and also gloves in their hands, which were now, before using the vector components, those animations were hard to create, but now with help of vectors they can be done a little bit more easily. We also have an example picture where we have considered a letter S, and we can see that the normal JPG images that we consider are not easily expandable for printing purposes, but when we use animations or graphics including the vector components, it is easy for us to resize the character or the graphic that we are using, and it also appears more clearly and vibrantly in the prints or in the banners. And we can see that it is a fundamental in computer graphics for rendering images and animation, as I've already told. Techniques like ray tracing and restoration involve calculating vectors. Then also have, we can use them to create different camera viewpoints, and lighting effect, shadow properties are also used by the application of vectors. And one last application we are going to be discovering is in mechanical engineering, which is one of the most basic branches of engineering, as we all know. Vector calculus is extensively used in mechanical engineering for analyzing forces, moments, and motions. For example, in designing machines or structures, engineers use calculus to determine the stresses and strains by analyzing the vector fields representing the force and displacement. Where in mechanical as well as in civil engineering, if we notice, it includes a lot of calculation regarding the force. And if we look into mechanical, if we look into automation or automobile industries, we have to notice that everything has certain horsepower, where power is also a component that is used. If we see that it provides, the vehicle provides certain torque, and torque itself is a vector quantity. So all these components, including force, or it could be displacement that takes place by a given automobile in certain time, all these acceleration and components include extensive use of vectors because they are vector quantities themselves. And last but not least, I would like to thank you all for joining me on this video. Thank you.